All right, so I promised to do a couple of simple examples using these equations of motion for 1D motion and assuming constant acceleration. So one situation where we might find ourselves in a approximately or near as makes no difference kind of constant acceleration situation is when a car is smoothly braking to a halt. All right. We're given, we're given that the acceleration of the car is negative 8 meters per second squared. And we're told that the initial velocity of the car is 28 meters per second, which is, right around 65 miles per hour or so. And we want to know how far does it go before stopping. Now, because where everything is moving in the same direction, then this how far does it go before stopping isn't ambiguous in terms of whether it's meaning distance or displacement or anything like that. This is just going to translate in terms of the objects we have in our equations of motion to delta x. Okay, so in other words, what is delta x? Now, whenever you're solving a problem, even one that's relatively straightforward like this one, you want to take the time to make yourself a little diagram. So I'll do that here, all in one fell swoop. I've got a little car with flames on the sides of it, and I've written down some relevant information, right? And the other thing that we don't have actually like written out in numbers in the problem statement, but is implied or is stated, is that we're interested in a final velocity of 0 meters per second. Now, that's a pretty mild example. I think if you read that question, you would pretty easily come to the conclusion that the final velocity, in terms of translating it into mathematical terms, the final velocity would have to be 0, right, for us to get the information we wanted. There are more subtle bits of implied information that we will see stated, and they will appear subtle at the beginning if you haven't had much physics, and once we've seen a few of these things, you'll get used to the idea that the information is not really being hidden, it's just being put in physical terms, okay? And the translation process of you looking at the text, figuring out what physical model applies and what information is given is an important part of learning physics. So anyway, this is a nice simple one, and when we look at this, we've got 1, 2, 3 knowns in the problem. And that should give us a warm and fuzzy feeling, because if you look at any one of these equations of motion, say that first one, you've got 4 terms in there. So if you know 3, you can get the 4th. And because we are looking for delta x here, and we are given 3 known quantities, then we have high hopes for being able to directly solve this problem without having to resort to any extreme measures. Okay? Now, at this point, we should be able to solve this all in one fell swoop. We shouldn't have to use like one calculation and then take the result of that calculation and feed it into another equation of motion to finally get our answer, right? If we appropriately pick the equation of motion that we want to use. Proper tool for the job, as always. So if we look down our list here and we look at the things that we know, we don't know time. That's the thing that jumps out at me, okay? And if we look at all 4 of these equations of motion, we've got time, we've got time, we've got time, and time. Time's everywhere, except in this equation of motion. And if we look at that, it has the thing that we want, it has a thing that we know, a thing that we know, and a thing that we know. So all we really need to do here is do a little bit of an algebra to solve that equation of motion for delta x, and then away we go. So let's do that. We'll subtract v0 squared from both sides. Okay. That gets this term over on the right all by itself. And then we can divide both sides by 2a. That cancels it over here. And we're left just with the thing that we're looking for on the right and all the rest of the stuff that we know on the left. When we substitute all of that in, so forgive me for not writing in the units here, but this is negative, oh, I'm sorry, look at me, okay. Final velocity 0, okay, squared, so that's just going to be 0. 28 meters per second squared, okay. And we'll divide that by 2 times negative 8 meters per second squared for acceleration, okay. So a couple of things here. Don't forget this minus sign, right? Because if you do forget it, then you end up with a negative number over here, and you're wondering how you got going backwards, right? Your delta x would come out to a negative number. Sometimes that's fine, particularly if you recognize, oh, I just missed a minus sign, so I'll just cross it out and be done with it. But in more complex problems, if you make an assumption like that, or rather you drop something like this minus sign in the numerator, and you go through several more steps, it might be a lot more subtle in terms of the mistake that then feeds into another calculation, which feeds into another calculation, and then suddenly who knows what you're going to be getting in terms of your final result or whether it makes sense. So be careful there, all right? A little bit of care up front can go a long way down the range. So if we take a look at this, we punch it into our calculator, we calculate our delta x. I believe we get delta x is equal to just under 50 meters. 49 meters, question mark? Let's check the next slide. Okay, so that does that. And you see a little bit of algebra here, and there's our answer, okay? Nice positive displacement, 49 meters, all right? Now implied here, probably should make it explicit, but implied here is that this direction is positive, and thus this direction is negative. And we kind of knew that that had to be the case, because if we have the car going this direction and it has a positive initial velocity, right, 28 meters per second, then we need to bring it to a halt, to reduce the magnitude of that initial velocity. Then we need a negative acceleration, like we've been explicitly given in this problem. All right, so there's one straightforward example of how to use these equations of motion. Let's look at another one before the end of this mini lecture, and that's one involving free fall. Now, we'll be talking about free fall more generally, and again and again and again, because it involves gravity, and gravity is certainly a powerful force that affects many aspects of our lives, and we'll return to it again and again. But this is our first exposure to it, unless you saw my earlier demo problem video. And this example is nice and straightforward, okay? So I have a rubber ball. I chuck it straight up into the air, and on the return, it collides with my head instead of my hand. And that means that, as I'm saying here, that it's 0.5 meters above the ball's release point, right? I release it here at my hand, and then it's whacking my head some distance above that when it returns. What is the ball's velocity as it collides with his head? All right, so I've, just so we know what's in our toolbox here, I've put our equations of motion over there on the left. We've got stick figure instructor here, chucking the ball upwards. We probably should make explicit that in our coordinate system that we're going to use here, that up is positive and thus down is negative. And you'll note that there's only two explicitly given pieces of information in this problem. Initial velocity, right? The velocity with which the ball leaves my hand is 8.9 meters per second. And the delta x for the entire trip, at least, you could think about doing delta x's to the top of the trajectory or something like that, but delta x for the entire trip is positive 0.5, right? Because it ends 0.5 meters above where it started. And that's it. However, as soon as the ball leaves my hand, there's nothing touching it except the air, and we're going to be neglecting air resistance for the immediate future anyway. And, well, that's it. The only thing touching it is the air. And so the only thing affecting its motion at that point, if we're neglecting air resistance, is the gravity of the Earth. And the gravity of the Earth, near the surface of the Earth, accelerates all objects towards the surface of the Earth, technically towards the center of gravity of the Earth, but towards the ground, down, towards your feet, at a specified rate, okay? I think technically the average over the whole surface of the Earth is 9.81, and I won't quibble about that too much. Okay, I'm going to use 80, and that's in meters per second squared, as all standard unit accelerations are. And it's downward in our coordinate system, right down towards my feet, down towards the center of the Earth. That's the implied piece of information here. We're not told that, but we should know, being good physicists, that as soon as this thing leaves my hand and my hand is no longer accelerating it from stationary to its initial velocity, well, then the only thing accelerating it is gravity. And so we have this nice constant acceleration that's acting upon it during its entire trip through the air, up to the top, back down until it hits my head. And then, of course, my head is applying a force to it that causes it to accelerate in a very different way. Okay? But we don't really need to worry about that. We're just talking about the ball as it is in so-called free fall, only under the influence of gravity. Okay, now that we have these three things, we again should feel pretty confident about our ability to solve this problem. And if you go through the equations of motion over here on the left, let's give them some numbers, okay? You'll notice that again, we do not have time. And so we can eliminate this one, and we can eliminate this one, and we can eliminate this one, and we're left with this one. Now, we're asked a slightly different question about this equation of motion, but in fact, the answer that we're going to be getting here is even more straightforward, algebraically, than what we had to do in the previous problem. Because what is the ball's velocity as it collides with his head? Well, that translates to what is the ball's final velocity? In other words, the velocity of it just before it whacks into my head, that instant, so that we can still consider it to be only affected by gravity, and thus the acceleration is constant, and we can apply all of these equations of motion to its motion. All right, so I'll sketch out the result here. We have this equation of motion. We put in our initial velocity of 8.9 meters per second. We put in our gravitational acceleration, and we put in our 0.5 meters for delta x positive. When we punch all of that in, we will get a rather large number. It may seem unreasonable, but when you do, remember that that is v final squared. And you need to take the square root of both sides to get the final answer, which is somewhere in the neighborhood of a little over 8 meters per second. I think it's like 8.3. And we'll see if I'm correct here on the next slide. All right. We'll make a couple of notes about a couple of things here to watch out for, but let me bring up the neater version of all of this. And there it is. Okay. So one thing that I forgot to stick into my hastily sketched out solution on the last slide there was this negative sign. Okay. If you punch this into your calculator, right? If you do this, take square root, it's probably just going to give you positive 8.33 meters per second. And that's the calculator doing what it does. Okay. But you do know, right, that when you take this square root, there's two possible roots, right? There's a positive one and there's a negative one, because the v final squared here could be negative 8.33 or positive 8.33, and you'd still get this 69.41, okay, that we get when we punch in all of our numbers. The thing is, as physicists, what we have to do is we have to say, okay, there are two roots, that's the mathematics, okay, and say, well, is this ball traveling down or up, right? Remember, this is up in our coordinate system here. And the answer is when it's traveling back down towards my head, right, our final velocity here, that instant before it collides with my head, it's traveling downward, so it must have a negative final velocity. All right? So don't lose sight of that. Okay? Always go back to the physical situation, and that will often inform you whether if there's some ambiguity like this in a problem, the physical situation should sort that out for you very quickly. All right? A couple of other things. Occasionally when people solve this problem for the first time, what they want to do is they want to say, oh, well, first I need to look at what happens with the ball as it goes from here all the way up to the top. And then once I know what's going on at the top, then I can figure out what's going on sort of during this second portion of the movement as it's coming back down towards my head. That will work, but you are doing a lot more work than you need to be doing. And the reason for that is, again, that when you have constant acceleration, and you go back to those definitions and you look at what displacement, this delta x, actually means, okay? Remember, it's only concerned with the final position and initial position. And the initial position we're free to call, 0 meters. And the final position, we're told already, is 0.5 meters above the ball's release point. So my hand was a half a meter below the top of my head whenever I released it, okay? And its final position will be right there, whacking me in the forehead or something like that, okay? So yes, you can do that. You can do two problems and figure out what's going on the way up, and you can figure out what's going on the way down, but you don't need to, as long as the acceleration or other parameters of the problem have not changed. All right, so keep that in mind. We'll wrap up this video right here, and next time we'll be into some more applications of these equations of motion. I will see you then.